In today's video, we are going to go over Kepler's 3 laws of planetary motion. Before we get started, please don't forget to subscribe to my channel, Step by Step Science. Get all my excellent physics, chemistry, and math videos. Please subscribe, click the notifications bell, give me a thumbs up, leave me a comment, and don't forget to share this video. In addition to that, I have a bunch of other teaching and learning materials that you can find at my paid teachers website. Whether you're looking for practice problems, notes, examples with all the solutions, some puzzles, some activities you can do with PHET simulations, all of that is available at my paid teachers website. The link is in the description below. And before we get started with Kepler's laws of planetary motion, let's just do a little bit of history. This was done a long time ago. It's amazing, 1500s, 1600s. And Kepler came right after Copernicus. And Copernicus is generally the person who gets credit for proposing a heliocentric or a sun-centered solar system or universe at that time. And he published a book that was called On the Revolution of the Celestial Spheres. And he published that in the same year of his death, which was 1543. And this is one of the diagrams from his book. You can see they have the sun in the center, and then there's Mars, Venus, and Earth, and the moon. And before this time, it was widely accepted that we had a geocentric or an Earth-centered universe or an Earth-centered solar system. But Copernicus was, of course, the first one who came up and proposed a heliocentric universe based on observations that he had made. And after Copernicus, in the early 1600s came Johannes Kepler, who we'll be talking about in this video, and he did a lot of work with the data that was collected by Tycho Brahe. He was a student. He worked at Tycho Brahe's observatory, and Tycho Brahe collected a lot of information on the orbiting planets, on the orbit of the planets, but he couldn't put it all together into a system, and Kepler was the one who put it all together, and he studied the orbit of Mars primarily, and he was the first one to come up with the idea that the planets moved in elliptical orbits, and also that the planets were kind of free-floating and not attached to some sphere that was rotating around some place, like, in this case, we're talking now about heliocentric universe, the sun. So he had elliptical orbits, and he was talking about the planets having free-floating motion, and that was done in the early 1600s. Now, we're going to go over each of Kepler's 3 planetary laws, and these are kind of like Newton's laws, where you have Newton's first, second, and third law. We have Kepler's first, second, and third law, and Kepler's first law says that the shape of the planet's orbits around the sun is an ellipse with the sun at one of the foci, and that there is nothing located at the other focus, and this is commonly referred to as the law of ellipses. Okay, ellipse is kind of like an oval. An ellipse is a plane curve that has 2 focal points. It has like 2 centers, so to speak. We can start by thinking about a circle. We have a circle that has a center, and every point on the circle is equidistant from that one center. So if we draw or put 2 points on the circle and we draw a line from the center to each of those points or to any point on that circle, then all of those points are equidistant from the center, and we call those distances the radius. That's the radius of that circle. Well, you can think of an ellipse as kind of a circle with 2 centers. Okay, it's kind of an oval, a flattened egg shape. It's called an ellipse, and it has 2 foci. Okay, one of those things is called a focus, and the 2 plural is called a foci. And as he said above in his first law, that the sun is at one of the foci, and there's nothing else really there at the other focus. Okay, so we have the sun at one location and nothing over here. But we do have a focus, and that's a point that we can put there, but there's nothing physically there. Now, one of the characteristics of an ellipse is that if we choose a point on the ellipse and we draw a line from one of the foci out to that point, and then from that point back to the other foci, that distance, if we add up those 2 distances, that distance is a constant for any point that we choose on the ellipse. So if we choose another point on the ellipse and we draw a line from one of the foci and then to the other foci, if we sum up those 2 distances for the blue lines and we sum up those 2 distances for the red lines, then those 2 distances will be the same, and that's a constant for any ellipse. All right, so that's one of the characteristics of an ellipse. Another characteristic of an ellipse is its eccentricity. And to get to that, we're going to talk about some of the anatomy of an ellipse. So we have an ellipse here. We have the two foci. If we draw a line through the two foci, right through the ellipse like that, we call that the major axis. And if we draw a line perpendicular to that, that goes the greatest length across the ellipse, we call that the minor axis. Now, when we talk about ellipses, we usually want to just talk about half of those things. So the distance from the center of that ellipse, the center being here, out to the edge of the ellipse, that distance we usually designate as A, and we call A the semi-major axis. It's half of the major axis. Then we talk about the distance from the center and then halfway along the minor axis, and that we designate as B, and we call that the semi-minor axis, like that. Now, another distance that's important when we talk about the characteristics of ellipses and its eccentricity is the distance from the center out to one of the foci. We usually designate that as C. It doesn't really have a name, but it's the distance from the center to one of the foci, or to one focus, like that. Now, when we talk about how oval or how squished or how not round an ellipse is, we talk about its eccentricity. The more eccentric that it is, the less round that it is, and the farther the foci are from the center, or the farther the foci are from each other. And eccentricity, we give the abbreviation as a lowercase e. Now, there's several different ways you can calculate the eccentricity. One of the simplest ways to calculate it is simply taking C, the distance from one of the foci, from the center to one of the foci, and divide that by the length of the semi-major axis, and that gives you the eccentricity of that ellipse. And you can see if you had a circle, okay, then this distance would be 0, and 0 divided by any number is 0, and that means that the eccentricity of a circle is 0. Okay, so if you have a round sphere or plane sphere and has an eccentricity of 0, then you know that's a circle. But the farther those 2 points get away, the more eccentric it gets, and the eccentricity of an ellipse is always going to be greater than 0, but less than 1. If you have it more than 1, then you're going to be talking about either a parabola or a hyperbola. Okay, so that's kind of the anatomy of an ellipse, and it's important to remember that the eccentricity can be calculated simply as the distance from the center to one of the foci divided by the length of the semi-major axis. All right, now Kepler did say that the planets' orbits are ellipses, okay, but they are elliptical, okay, but they do have a pretty low eccentricity. Most of them, when you see them drawn to scale, or when you see the orbits of the planets, they really look circular. I mean, Mercury has a little bit of a higher eccentricity. Of course, Pluto will include in this, also has a high eccentricity. But you can see that the eccentricity of most of the planets is pretty low. So they look really much more like circles. They're not really flattened, as I showed you in the previous slides. They look much more like circles, but they're not circles. They're actually ellipses. And when we talk about the planetary motion, we have to be very careful when we talk about their shape, and we consider them to be elliptical. All right? Okay, now we're going to go over Kepler's second law of planetary motion. And Kepler's second law of planetary motion says that a line drawn from the sun to a planet will sweep out equal areas in equal intervals of time, and that is commonly known as, you guessed it, the law of equal areas. Okay, now this is the way it works. Here we have our elliptical orbit around the sun, and this could be one of the planets or any of the planets, and let's just choose Earth. And let's just say at some point in time, Earth is approximately right there. And we're going to draw a line from the sun out to the Earth on its elliptical orbit, and then we'll say the Earth is orbiting the sun in this counterclockwise direction, and you can choose any time interval you want. It could be a day, a month, a year, an hour, whatever you want to do. Let's just say in this case that it's 1 month, and 1 month later the Earth is going to be right there at P2, point number 2, and that means that that line drawn from the Earth to the sun at point 1 will sweep out some area as the Earth moves to point number 2 1 month later, and that is some area just like that. Okay, that's the area that's swept out by the orbit of the Earth as it goes around the sun. Okay, now we're going to say let's choose another place for Earth. We could choose it's over here now. And we're going to draw a line from the sun to the Earth at that location of its elliptical orbit. And then we're going to choose an equal time interval. It says right here, equal time interval. We'll just say 1 month again, of course, because that's equal to 1 month. And then 1 month later, the Earth is going to be right there at position number 4. And its orbit, the line drawn from the sun to the Earth, will sweep out some area in that time interval. And then we have the area that's designated by that red section like that. And as Kepler's second law says, that area for an equal, it will be equal for any time interval. So that means that the red area that's swept out by the planet over here and the blue area that's swept out by Earth over here, those two areas are going to be equal to each other. The planet will sweep out equal areas in equal time intervals. All right, now you'll notice that the distance that the Earth traveled over here is less than the distance traveled over here. And that's because at this location, the Earth is farthest away from the sun, and it's going to be traveling slower. At this location over here, the Earth is going to be closer to the sun, and therefore it's going to be traveling faster. So the velocity, the speed of the planets around the sun is not constant. It's changing. And when you're farther away, and when you're farthest away, we call that aphelion, then the planet is going to be traveling the slowest. And when you're closest, it's going to be traveling the fastest. And when it's closest, we call that perihelion. Okay, you can see I think of it this way, is away, that's the farthest away, that's aphelion. Now you'll notice that both of these terms have this helium in it, and that is because this is when we talk about the planet's orbits around the sun, because that refers to the sun. When we're talking about the Earth, we call it apogee and perigee. Okay, so just keep that in mind. There are different terms depending on which the central object is, but for the sun, it's aphelion and perihelion. Okay, that is the law of equal areas. Now we're going to go over Kepler's third law of planetary motion, and we're going to talk about some of the mathematics of the planet's orbits around the sun, because Kepler's third law states that the square of the planet's orbital period t is proportional to the cube of the length of the semi-major axis A of its orbit. Remember, t, capital T, is the abbreviation we give for the orbital period, and A is the abbreviation we give for the length of the semi-major axis. And we can summarize that statement as t squared is proportional to a cubed. Now we are going to use two of Newton's laws of motion, which he published almost 80 years later, to show that Kepler's observations were correct. And we're going to use Newton's second law of motion and Newton's law of universal gravitation. If an object is traveling on a circular path, then we can write Newton's second law like this. And the force that keeps it on that path, the centripetal force, is equal to the mass of the planet times its velocity squared divided by the distance between the sun and that planet. Now, that force comes from Newton's law of universal gravitation, which we can calculate as g, the gravitational constant, times the mass of the sun, times the mass of the planet, divided by the square of the distance between them. And we know that these two forces are equal in magnitude. So we can set those two equal to each other, and we get this equation. Now we can simplify this equation because you can see we have the mass of the planet on both sides of the equation, so that's going to cancel out. And we also have r on both sides. Here we have r and here we have r squared. That's going to allow me to cancel one of those r's. So on the left-hand side, when I cancel out the mass of the planet and this r, I'm simply left with velocity squared. On the right-hand side, I'm canceling the mass of the planet and one of these r's, and that means I'm left with the velocity squared is equal to g, the gravitational constant, times the mass of the sun divided by the distance between the sun and the planet. Okay, that's the first part. Now, in the second part, you can see we want to find out the relationship between the orbital period t and the distance from the planet to the sun. Now you can see in this equation, r and a are going to be analogous to each other. So we already have the distance in this equation, but we don't have the period, we don't have the time in this equation. So somehow we have to get the time into this equation. We can do that with the velocity. Because we know the velocity, we can calculate the velocity of the planets as the distance it travels divided by the time, because the distance divided by time is going to be velocity, meters per second. Now, this 2 pi r is the circumference of the planet's orbit around the sun. Okay, so this is the distance that it travels, because 2 pi r is the equation for the circumference of a circle. And then we can divide that by the time, and we take the distance divided by the time we get the velocity. So I can substitute this term in here for the velocity. I have to remember to square everything. Now, 2 squared is 4, pi squared is pi squared, r squared is r squared, and t squared is t squared. So on the left-hand side of this equation, now I have this term. And I'm going to set that equal to the original term we had over here, which is g times the mass of the sun divided by the distance between the planet and the sun. Now what I'm going to do is I'm going to cross multiply. And when I cross multiply, I'm going to multiply this by r, and I get 4 pi squared r cubed. And I'm going to take the t squared and multiply it by gms. And so I get t squared is equal to g times the mass of the sun. Now I am going to rearrange this equation so I have the ratio of r cubed to t squared. So I'm going to divide both sides of this equation by 4 pi squared, and then I'm going to divide both sides of this equation by t squared, and that will give me on the left-hand side r cubed divided by t squared, and that is going to be equal to g m divided by 4 pi squared. So all I did was divide both sides by 4 pi squared, and then both sides of the equation by t squared, and I end up with this equation. Now you can see that on the right-hand side of this equation, all of these terms, g, the mass of the sun, 4, and pi squared, these are all constants for our solar system when we're talking about the planets orbiting the sun. G is not going to change as a constant. The mass of the sun is not going to change. It's a constant. 4 and pi squared are not going to change. So that means that these terms will always be a constant, and this is what we call Kepler's constant. For any planet in our solar system, r cubed divided by t squared is always going to be equal to this value. So that means that r cubed divided by t squared is also going to be a constant, and that is Kepler's constant. And we can write that like this. Kepler's constant is equal to r cubed divided by t squared. Now, when we're talking about elliptical orbits, we can substitute in here. When we go back to elliptical orbits, we can substitute a in here for our r, and we get that Kepler's constant is therefore going to be equal to the length of the semi-major axis cubed divided by the period squared. And this is the equation that we use to calculate Kepler's constant. Now I'm going to show you what we mean by Kepler's constant and Kepler's third law for our solar system. Remember, Kepler's third law states that the square of the orbital period is proportional to the cube of the length of the semi-major axis. And we showed you, or I showed you, how to calculate Kepler's constant. And Kepler's constant is the cube of the semi-major axis divided by the square of the period. Now here we have the data for our solar system. These are, of course, all the planets in our solar system, and we are going to use the length of the semi-major axis in astronomical units. You could use different units if you want, for example, meters or kilometers. But when Kepler did his work, he measured the length of the semi-major axis in astronomical units. 1 astronomical unit is the distance from the sun to the earth. That's why it says 1 right here. That's 1 astronomical unit. Mercury and Venus are closer to the sun than the earth, so they're less than 1 astronomical unit away from the sun. And the other planets, Mars through Neptune, are farther away than the earth. They're farther away than 1 astronomical unit, and that's why these values are greater than 1. So Kepler used the length of the semi-major axis in astronomical units, AUs. He used the period in days. Once again, you could use it in seconds or hours or something else, but he used astronomical units and days. And if you take the cube of the semi-major axis measured in astronomical units and divide that by the square of the period measured in days, you will come up with Kepler's constant for our solar system, and you can see that that value is the same for all of the planets in our solar system. about 7.5 times 10 to the minus 6 AU cubed divided by day squared. So you can see for each planet, you get the same value. This is Kepler's constant for our solar system. And you can calculate Kepler's constant for any object that's orbiting the sun, and you will get the same value. You can calculate Kepler's constant for any planetary and moon system, for example, Jupiter and its moons, Saturn and its moons, Earth and its moon, or any of its satellites, and you can find Kepler's constant. You will get a different value for Kepler's constant. Each orbital system has its own Kepler's constant, but if you were to calculate Kepler's constant for Jupiter and its moons, you will get, of course, a different value, but you will get the same value for all of its moons. Okay, so there you go. That is everything that you need to know about Kepler's laws of planetary motion. Thank you so much for watching. I hope you enjoyed that video. If you did, please do all of the following 5 things. Subscribe to my channel. Get all my excellent physics, chemistry, and math videos. You should click the notifications bell so that you don't miss anything. You should give me a thumbs up. You should leave me a nice positive comment. And don't forget to share this video. Thank you so much for watching. We'll see you in the next video.